Hi everyone, I'm Lior and this is Arnon, and we are full stack developers at Monday.com. And we want to talk with you today about client performance. And the reason is that we really scaled a lot in the past 2 years on Monday. And as we added many capabilities to our system, things really got complex and our performance degraded. And each time it happened, we worked a lot to improve it. So we really learned a lot during this process. And the second thing is that we believe that it's really important to optimize your performance, but it's also important to know how to measure it. And we want to show you some ways to do it. Just a short question. Can you tell the difference between those two products? No. Okay. So this was about the difference for us. Okay. So this was the difference in cost for an entire year. Luckily, we were fast enough and improved it, so we still have this money in our pockets. But just to demonstrate how much performance is important, and it's not just something that is nice to have, it's really important to our user and our users' experience. And okay, so a bit about us. I'm Lior again. I'm part of Monday's growth team, which is in charge of taking the existing product and optimize it in terms of user adoption. And Arnon is part of the platform team, which is in charge of taking the product and develop all the core features of Monday. This is our stack. We work on the client side on React Redux frameworks for the past 2 years or so. We really got to know it very well. And this is our product. For those of you who don't know it, we actually want to show you that because we're going to give some examples during the lecture. A really nice one from the product. As you can see, this is our board. It consists of many rows and many columns, each column with different types. And this is how it looks like when you have many columns and many cells. Each cell has a lot of complexity and functionality. And you can maybe understand already how difficult it can be to keep it with good performance. Okay.
So we'll start with the main players in web app performance. The first one is the JavaScripting. It's all the JavaScript calculation that the browser needs to do in order to calculate the process. We have the rendering. The rendering is the process that the browser needs to recalculate all the styles of the rendered elements and to determine the positions and the sizes of the elements. The third part is the painting. It's the process that the browser filling the pixels to the screen. So if we want to measure the performance, we can, for example, we took it from the Chrome DevTool. We scroll down the page, we record the screen from the performance tab, and then we can analyze the results. We will dive into it later to show how we can do it in an easy way. So in general scripting, JavaScript is very fast, and rendering and painting is slow. DOM manipulation is also fast. We can modify the DOM, we can search element very quickly, but the consequences, such as rendering and painting, is slow. So we want to find ways how to reduce these slow operations. So we have the concept of virtual DOM. Virtual DOM is an abstraction of the DOM. We can build 2 versions of the DOM, for example in JavaScript, and then we can compare them in order to find the minimal diff in order to find the minimal diff in order to update the DOM itself. So in order to do that, we need to compare the 2 different trees. We can see here that we have the virtual DOM. We have the updated virtual DOM after the process that we did. For example, we remove the first element in a list, and then we find the minimal diff and update the actual DOM. So the best algorithms that are running today in order to compare 2 different trees are running in O of n power 3. This is the best algorithm that are running today. So for example, we have an optimal page that contains around of 1,500 DOM nodes. And for example, you can check it in the audit tab in the Chrome tool. You can scan the page and we can find how many DOM do you have, and more analytics, such as diagnostics and more. And for example, we scanned our page, a regular page in Monday, and we saw that we have 5,000 DOM nodes. And we saw that optimal page contains only 1,500 DOM. So if we calculate all together, we saw that if we are using the naive algorithm, we will find that we have around of 3 billion comparisons. It's a lot, and we need to find a way to reduce it.
Okay, so how can we reduce this number of comparisons? We saw that we have the virtual DOM. Okay, we have the old DOM, and we just did maybe a small update, and we created a new virtual DOM, and we want to compare them. And obviously, 3 billion comparisons is not optimal at all. So there is where our framework can help us. In this case, it's React. We want to dive into it and talk how it works there. But actually, a lot of client-side frameworks work with this concept today. Okay, so what React basically did, it created the reconciliation algorithm. What's the reconciliation algorithm? It's a heuristic algorithm. It means it runs under certain assumptions, and with these assumptions, it can run in O of n running time. So what are the assumptions? And let's see how it can help us as developers to know them and to maybe program better. So the first one is pretty simple. It just means that different types will create different subtrees. So on the left, we can see we have the old DOM tree with a div on the top. And on the right, we have the new DOM tree that React created after the update. And once React recognizes that there is a different DOM type on the top, it will throw away the old DOM and recreate the entire subtree. Although we can see that the counter inside didn't change, and of course it's not efficient at all. The second assumption is that React will be given by the developer a key to identify certain elements, okay? So once it's created the new virtual DOM, it will look for the key in the old DOM, and it will know to tell if it was existed or not. And if it was not existed, it will regenerate this DOM element. But now we want to know how should we choose its key props. So if we have only 1 or 2 elements, it's pretty easy. But what happens if we have a list of items, okay? If things get a bit more complex, and let's see some cases. Okay, so this again is our board. It's our product. You can see we have a list of items, 3 items in this case. And we want to delete the first element. And we want to give you some hunch or some feeling about how this can really have a strong impact on our performance. By which key do we choose? So let's see some example. First of all, once we render a list, React will, and we didn't choose a key, React will throw this warning and say, hey, you have to choose some key, okay? You need to choose to give each one of your elements at least something. So what do we all do in this case? Some React developers? Index, awesome. Okay, that's true. So we have our rows in our hand, and we render each one of the elements. And the easiest thing is, obviously, we usually have the index in our hand, and this is what will give the component. In this case, we want to look and see what actually React will do in this case behind the scenes, and maybe why it wouldn't be the best thing. So this is the old virtual DOM. Okay, let's say this is what React created, and you can see because we gave the index key, so we have 1, 2, 3. Let's say we're counting from 1, and after we delete the first element, React will regenerate the tree, and now it will give it the first element again will get the key 1, and the second element will get the key 2. Now React will need to compare between these 2 trees, and when it will look for the key 1 at the old tree, it will find it as this element. But because these are 2 different elements, it will update the first element with the props of the old element, and the same for the second element. So we have already 2 updates, and it will just erase the third element from the previous list. Okay, this is obviously inefficient, okay? And what happened here, we had 2 updates and 1 unmount. And this is only for 3 elements, okay? So imagine for maybe 1,000 rows, we have 1,000 updates, which is already feels not efficient at all. This is just a snapshot from the Chrome DevTools that Arnon showed you before. You can see the React sequence, render sequence, and you can see there that it actually states that we had an update for each one of this render sequence. Each render sequence is for a single row, and it took us 18 milliseconds per update. The second one, which I'm already telling you, it will be probably better, is to choose really a unique ID, okay? So usually these rows or these items that we render, they represent some kind of maybe a DB entity or something, and we can use this ID of this entity as the key of the object. In this case, we have the old virtual DOM. Each row will get the ID of this row as the key. And when React recreates the new virtual DOM after the deletion of the first element, the keys will be identical to the keys in the old DOM. So now when React will look for the first key in the old virtual DOM, it will find the right element. Same for the second one, and now it will throw only the first element that was actually deleted. Okay, so this time we had 0 updates, which is crazy. Okay, so again, in the first example with the index, we had 18 milliseconds, which sound maybe not that much, and 0 milliseconds in the unique example. But again, when we talk about 1,000 rows, so it would take 1.8 seconds only to delete 1 element. So think about how impactful it would be to save it in terms of user experience, which is a very, very simple action.
So now we want to take you to a little journey, the performance story of Monday.com. It started in 2016 when we decided to write the first boards. We decided to write it in Backbone. Backbone is a lightweight library that gives you the ability to modify the DOM and to manage your client side. At the beginning it was great. It has good performance and all was good. But afterwards, we have added a lot of new functionality to the DOM and to the boards itself, and we experienced a decline around the middle of 2017. So we understood that we need to do something in order to improve it. So we decided to do a POC in React in order to prove that this is the right direction for us, and we took 2 days in order to do that. After 2 days, we understood that this is the right direction, and we decided to rewrite the board in React. What are the main reasons? The first one was that it was easy to maintain. Each component that we built, we can use it all around the place, all around the system. And second, it has good performance by default. As we saw, React implemented the virtual DOM, and it was great for us. So after we have added all the functionality to the boards, we saw that it's still slow to scroll and to interact. And we understand that we need to find a way to improve it. And why it was slow? Because of 2 major issues. The first one is that we have a lot of elements in the list. As Lior showed, we have a lot of elements. Each row can contain a lot of complexity, and these are the main issues. Let's take, for example, the status cell. It's one type of column that we have in the system. The status cell contains 10 DOM nodes for each status cell. In addition, it has 26 event listeners. We took this screenshot from Firefox DevTool. It's an easy way to find how many event listeners do you have in the DOM. And this board, for example, has 9 status columns and 100 rows. And if you calculate all together, we get 9,000 nodes and 23,000 event listeners. As we saw, optimal web page contains 1,500 DOM nodes. So what are the implications of heavy lists? The scroll is slow. The interaction between elements are heavy. So we want to improve it. So what we did, we decided to change the, we decided to choose windowing instead of to render all the list. And windowing is a concept that gives you the ability to render only the visible elements in the screen. The benefits of windowing are that we reduce the number of elements and we're reducing the number of event listeners that we have in the DOM. For example, we decided to implement it for those days with React Virtualized Library. And it works like when we scroll down the page, each new element that should appear in the screen will be created in the end of the list. And the first element that should be deleted will be deleted from the top of the list.
Okay, so as Arnon showed us, we use React Virtualize. Okay, every time you scroll, a new element is on the bottom, and the first element on the top is being erased. But we want to show you some use cases and how we actually used it in Monday.com. And the most obvious one is scrolling. Okay, so it improved our scrolling. Now we have, instead of for 10,000 maybe DOM nodes in the due to the list, we have only 10 rows inside our screen. So we have probably about 500 DOM nodes in this board. So that was I was scrolling, and the entire DOM interaction became a lot faster. The second use case we want to show you is something not that trivial about windowing, and it really can benefit us a lot, and it did help us in this use case. So this one is about the bolt switch, okay? So we showed you before, we have this board. This is our main entity. And on the left, you can see we have the list of our boards, okay? So a user can have maybe 100 boards, or maybe 1,000 boards, 500, a lot of boards. And it's not that easy to navigate them on this list on the left. So we created the bolt switch. The bolt switch is just a quick navigation component. The items are arranged by the recency. And the idea is that once you click to open the bolt switch, you want it to open really, really fast. Okay, you don't want to wait. You already have the entire data inside on the client side, and you just want it to write open and move to your next board. Just to demonstrate how it used to work. Okay, so on the left you can see what happened without windowing, and what happened once we added windowing. Okay, it actually took us 3 seconds to any time we open the bolt switch, which is a lot. Okay, this is the quick navigation component. You just want to switch a board, you just want to see the next one, and it takes you 3 seconds to open. And the crazy part here is that, again, the entire data is already in the client side. We don't have any Ajax call. We don't go out to the server. We already have it. So we want to see what actually caused this overhead. Okay, so let's analyze what happened. In this case that we showed you, we have 1,000 boards, and we have a list in this size. And once we clicked it, React needed to render 1,000 items at a single moment, okay? So without windowing, we needed in a single moment in time to render 1,000 mounts. Even if so they had a really fast mount or render function, it still took us 3 seconds to render. In the other case, with windowing, we only needed to render the ones that were mounted and were viewable on the screen. So for 15 items, it was very, very fast. The overall time in this case was 2.93 seconds and 200 milliseconds for the second case, which is a crazy improvement, okay? 13 times faster. Okay, we also like to measure our impact on users and what actually we save them. So you can see we have 8,000 users using this component every day. And we just saved them 2.7 seconds for each opening. Okay, so you can say we actually saved over 6 hours a day to our users, which is a crazy impact. And I think it only took a few hours to implement this windowing concept on this small component. Okay, so we started with Backbone, we then moved to React, and we implemented windowing, which was amazing, which was much faster for scrolling and everything. But it was still not enough for us, okay? So we felt that it's still a bit heavy. What we saw before, Arnon showed you that the way that virtualized work is that when you scroll the screen, every time a new row is entered the screen, virtualize actually need to mount another element on the bottom and remove the element on the top. This is very inefficient, okay? So what actually happens here is that React Render is called for each element that added on the bottom, and every time we remove an element from the top, we need to recalculate the styles of all the elements in the list. This is obviously not efficient at all. But how can we tackle it, and what we did in this point in time? So what we did was the light render, okay? The idea is that to build a minimal version of the component for each component in the list, okay? Only the representative version. So the idea is that while we scroll, we don't need the entire functionality, okay? Of each cell. For instance, this is the status cell we saw before. You can click it, you can add a note, you can hover it and change the colors and everything. But while we scroll, we don't need any of this functionality. So what we want to do is to build a minimal version that we can only see this in this version, the cell and its content. So if the old status cell, the full status cell, used to have 10 DOM nodes and 26 event listeners, we want to save this. So how can we minimize this, for example? What we did is we showed you this note thing before. Okay, you can click on the top right corner and you can add a note, but again, we don't need it. So this entire DOM nodes can be eliminated from the component. Okay, so we're already down from 10 DOM nodes to 6. The second thing we did is that we don't need any event listeners. So we don't want to check if we hover the component. We don't want to click it. We don't want to right-click it. We don't need anything while we scroll. So we just got down from 26 event listeners to 0 for only one element. Okay, so now we have the light component. We have a light row. But how do we actually implement it? So this is just nice to see. We use a React enhancer for those of you who know the concept. The idea is it's a component that is wrapping our cell component or our row component. And once we scroll, we first mount the light component only. Okay, so if we scroll, only light components are getting mounted. Once we stop scrolling, after a timeout of, in this case, of 1 second, we render instead of the light component, we render the full component with the entire functionality. Okay? And again, let's measure the impact we actually did here. So the areas we want to focus is the scripting, what happened, and what happened with the recalculate styles. This is again the React render sequence, and you can see that with the full render, each component took us 33 milliseconds to render, okay? We had more DOM nodes, more event listeners, maybe more actions that happened on the render, and it was very heavy. But with the light render, it took us only 19 milliseconds to render. In terms of recalculating styles, so again, when you remove the first element in a list, so we have the entire CSS rules in our browser, and they need to be implemented to the entire elements in this list. What happened in this case? We needed to implement the entire CSS rules for 1,700 elements for the full renderer, and only for 900 elements in the light renderer, which also a great improvement. Overall, the full render took us 500 milliseconds to render, and for the light render, it took only 230 milliseconds, which is a 54% improvement. It was great, and we did felt it an amazing improvement while scrolling the list.
So, as Lior said, we saw that we implemented the React boards, and then we have added windowing and light components, and the performance was good. And then we have added a lot of new functionalities to the board. For example, let's take a look on the column center, the new column center that we have added. Now the users can add a lot of new columns that we didn't have before. So this example is from a real client that built his board, his use case, and we saw a lot of new columns that he have added. And the board this board is a real use case and very heavy to interact. So after some time, we saw that we have another performance degradation, and we need to solve it. We take a look on a large board with a lot of new columns, and we saw that the board is very, very heavy. We can't scroll down easily, and the interaction is very slow. So what we do, we took another 2 days, more than 2 days, but a number of days in order to do a POC, to build a virtualized grid. The difference between a virtualized grid and virtualized list is that in addition to the windowing of rows, we are windowing also the columns. So it was very good for boards with a lot of columns, but it didn't affect boards with a few columns, as we expected. So we thought that we solved the issue because we improved the large boards, but as we saw, we started to get a lot of complaints tickets about the performance, not only for boards with a lot of columns. And for example, this board is a board that has only 11 columns, and the scroll is not enough for us. So we shifted into crisis mode, and we understood that we need to find a solution for that. We started with the investigation in order to find the biggest bottleneck that we have in the system. So we dive into React Virtualize, and we found some pitfalls. We saw that the major part that we need to solve is that while scrolling, as we said, we create and remove a lot of elements all the time. We scroll down. We saw that mounting and unmounting is very hard for the browser to do. The scripting and the rendering time took a lot of time. And in addition, because we are removing all the time elements from the DOM, the garbage collection should work a lot. And it can cause also a memory leak. So we understood that React Virtualized we got a dead end, and we need to shift to something else, and we find the recycling views concept. So what is the recycling views? Before that, we will show how React Virtualize again, just to remind how it works. We remove the first element in the list in order to show the last element and to create it. So recycling is the concept of, instead of remove and create new element, we will use the same element in the list. You can see in the video that while we scroll down the page, we just replace the elements, the existing elements, the content of them, instead of create a new one and remove the old ones. So what are the differences between React Virtualized and recycling views? So in terms of mounting, we recorded the screen and saw that in virtualized list, each time we scroll down the page and we need to insert a new element to the DOM, it took us almost 20 milliseconds. And if we use recycling views, we just need to update the element, the existing element, and it took us almost 9 milliseconds. In addition, in terms of recalculate styles, we saw that in virtualized list, once we remove the first element in the list, we need to recalculate all the styles of the elements. We saw that we affected 900 elements. And in recycling views, we just affected only 32 elements because we just update the new the new element that replaced the existing element in the DOM. So the total duration that we improved, we saw that virtualized list took us 230 milliseconds, and recycling views took us 35 milliseconds. That's amazing because we improved 75% improvement. So now we can see how it affects our user in terms of user experience, and we got this one. This is in the left side is the old one that uses a virtualized list, and the second one is the old one that uses recycling views. It's much faster, and it's amazing in terms of performance. So eventually, we experienced performance degradation in November 2018, and in the end, we increased the performance, and now we are here. We know that we will have more performance degradation, and we need to find more solution in the future. But now the performance is very good, and we are happy for that. Thank you for listening.